Let him come.
Огонь по готовности! Give me another shot. Perseverance is the key. Objective. Barriers on I'm under attack. Get in there.
composites being stiffer than aluminium, meaning it takes more force to deform the same volume of material. But critically, 787 wings are not the same shape as their aluminium counterparts. This ability to withstand greater bending allowed engineers to make the 787's wings with a much higher aspect ratio. Aspect ratio is the ratio between the wingspan and the mean chord, or wing width. A high aspect ratio would be a long skinny wing like a glider, while a low aspect ratio would be a delta wing of a fighter jet. A traditional airliner has an aspect ratio of about 9, like the 787's predecessor, the 777, but the 787 has a massive aspect ratio at 11. This is what causes the 787's wings to flex so much during flight. Composites are actually stiffer than aluminium, but their ability to withstand high deformation allowed the engineers at Boeing to create a much higher aspect ratio wing, a longer, narrower wing that would bend more.
Goodbye, roaming fees that rack up overseas. Hello, automatic coverage when I'm exploring the world. Hello, Google Fi, a phone plan that can.
Hey, congratulations on your purchase of the maintenance.
But this comes with some huge benefits. The planes with the highest aspect ratio are gliders. For an unpowered plane, the highest priority is minimizing energy lost to drag. This allows the glider to stay in the air for extended periods with no engine. These types of aircraft typically have aspect ratios greater than 30, and these aircraft have the lowest drag penalties as a result of vortex drag. This is the drag caused by air mixing from the high pressure zone under the wing with low pressure air above the wing, forming vortices at the wing tip. By spreading the area of the wing over a longer span, we minimize the pressure that drives this mixing at the wing tip, and thus minimize the energy lost to the vortices. Normally, higher aspect ratio wings have lower internal volumes. For an unpowered glider, this isn't an issue, but for a plane that needs that storage space for fuel, it is. Less storage volume for fuel means lower range, and one of the primary goals of the 787 is to be an efficient, long-range aircraft, capable of allowing airliners to open new routes that were once deemed impossible. Thankfully, modern planes like the 787 use a new kind of aerofoil, the Supercritical Aerofoil. Older aerofoils look something like this, a reasonably symmetric design with a sharp nose and gentle curves on the upper and lower surface, and this is a supercritical wing. The leading edge is blunter with a larger radius, the top is relatively flat, and the lower portion has this strange cusp at the back. This aerofoil has much more useful internal volume thanks to its blunt leading edge and larger thickness to chord ratio, helping solve our low internal volume problem associated with high aspect ratio wings. The Supercritical Wing was first tested by NASA on a modified TF-8A Crusader, and you can really see the similarities in design ethos between the experimental plane's sleek wings with the 787. But increased internal volume is not why NASA developed the Supercritical Wing. NASA developed it to delay the onset of shockwave formation over the wings. When air travels over a wing, the air on top accelerates. This means that even though the plane itself might be traveling below the speed of sound, the air over the wing may break it and create a shockwave. This shockwave decreases lift and causes an increase in drag. This kind of drag is called wave drag, and planes need to fly below the speed this occurs at. The speed is called the critical Mach number. The Supercritical Wing was designed to increase the critical Mach number. The flat top of the Supercritical Wing means the air does not accelerate as much as it would over a classic aerofoil. Of course, this causes a loss in lift because that fast-moving air is causing a drop in pressure on top of the wing. To compensate, supercritical aerofoils have this concave curvature underneath the wing, which causes an increase of pressure there to compensate. This increase in pressure does not affect the critical Mach number, while the larger radius of the leading edge increases the lift generated at high higher angles of attack. This is because air struggles to follow the tighter turns of a smaller radius leading edge, which causes earlier flow detachment and stall. The larger radius delays this flow separation. This aerofoil shape changes continually as you travel the length of the wing, twisting and curving in computer-calculated precision, optimizing the wing shape to be as efficient as possible, and composites provided the engineers with the confidence that these shapes could be manufactured. The skin is simply laid down on a mold with automated tape laying once again. We don't have to beat metal into shape each and every time we want to recreate these delicate curves. The fibers of the wing have even been laid in specific patterns to tailor the stiffness of the wing in different areas. This means the wing deforms exactly as the 787's engineers wanted to as it gains speed. So the wing shape actually changes during flight to better suit the needs at different speeds. This is called aeroelastic tailoring and is the forefront of state-of-the-art aeronautical engineering today. The 787 also features a novel device designed to reduce turbulent flow over the tail of the aircraft. Two types of flow states exist in aerodynamics. Laminar flow occurs at low velocities and is characterized by fluid layers flowing smoothly over each other in neat, orderly layers. Laminar flow is predictable and non-erratic and does not create significant drag. Turbulent flow is far more common, but still very little is known about how to predict its behavior. It is very difficult to control because of the formation of small vortices called eddies in the flow, making the flow highly erratic. Turbulent flow occurs at higher flow velocities and causes a significant increase in drag. At cruising speeds, 80 to 85% of the speed of sound, turbulent flow is ultimately unavoidable, but we can work to minimize it. Boeing has developed a technology that helps them delay and control the formation of turbulent flow called hybrid laminar flow control. Details on their implementation of the technology are sparse. This technology is capable of reducing fuel burn by as much as 20%.
Traveling to Route 66. Prepare to attack. Select your hero.
We're all soldiers now.
Get back!
Stick to the plan, and if you get into trouble, I'll bail you out.
Attack commences in 30 seconds.
Hello. Keep the skies clear for me.
Try not to get yourselves killed out there.
Five, 4, 3, 2, 1. Attack commencing. Escort the payload.
Payload in motion. Stay. I'm not a young man anymore.
minutes. Cease your resistance.
Activating self-destruct sequence.
I've got you in my sights. Resistance. Get over here and heal up. I'm on fire.
Behind the back. 60 seconds remaining. The payload has reached the checkpoint. Crash
Heal up here.
Get behind the body.
Wait, got you in my
Activating self-destruct sequence. Mega activated.
This old dog's learned a few tricks. I've got you in my sights. I love the solar pulse missions in the morning. My tactical visor is charging.
Damage increase.
Feeling spry. Oops. Tactical necessity.
Don't rest me.
Back in the fight.
Push, push.
resistance. We're leaving the winner.
I don't quit till the fight's done.
Time. Heroes never die.
Nanoboost administered. Team up for special attack.
I've got you in my sights. I've got you in my sights.
Score 3-0. Switching sides. Prepare your defenses. Select your hero.
We're all
combat routines. Optimizing strategy. Attackers incoming in 30 seconds.
What are you looking at?
See you in the air.
Attackers incoming. Stop the payload.
This is not your time. I recommend moving behind my
Everyone, heal up.
You rest.
Junkrat left side.
Your battle continues.
This old dog's
Pull back out of that.
tricks.
Don't peek him.
Back up, back up.
Get ready for a show. Heroes never
Spit out,
die.
spit out.
He fell.
Let's get you back in the fight.
Team up for special attack. Our heroes ready. Cease your resistance. For your safety.
Damage increased.
Feeling spry.
I recommend moving behind my back. 60 seconds remaining. Please move behind the barrier.
Got you in my sights. Come here, get stabilized.
I recommend moving behind my barrier.
This will help.
Heroes never die.
I've got you in my sights.
Oh, sorry. Junk left side.
Back up, back up. Back up, one more push.
Overtime.
This old dog's learned a few tricks.
Enemy in my sight.
Get over here, heal up.
Nice.
Victory. Play of the game.
I've got you in my sights.
Yeah.
So, companies are keeping their research extremely secretive to keep their competitive advantage. Here's what we know. In the late 80s and early 90s, NASA and Boeing began investigating a suction system, the 757, that would draw in boundary layer air. That is, the layer of very slow-moving air that clings to the surface of moving objects. The outside skin was permeable to air through tiny perforations, too small for the naked eye to see. Manufacturing the permeable surface while also keeping the tiny holes clear of debris is one of the many challenges with this technology. The outer and inner skin were then attached to an elaborate plumbing system that was connected to a turbopump which sucked air from the boundary layer of air that would form along the plane's surface. By doing this, they could drastically delay and reduce the size of the turbulent flow, and in turn, reduce the drag on the plane. There is no space for this ducting system inside the wings of the 787, but from what we do know, it is inside both the horizontal and vertical tails. However, the only clue of their presence are these tiny doors, whose purpose are a mystery to me with little to no information available online, a testament of how advanced this plane is. Composites give plenty of advantages, but it does come with some disadvantages. When we examine the plane's composition, one material jumps out at me. 15% of this plane is titanium. That's much higher than normal. Titanium is an expensive material, so they must have had a good reason to use it over aluminium.
Hey everyone, I'm Ashley from Amaze, and this is it. Last chance to win this stunning 4-bedroom greenhouse in beautiful Austin, Texas. Or
Aluminium is typically corrosion resistant. When it's left on its own, but when it is placed in direct contact with carbon fiber composites, something strange happens. The aluminium begins to corrode incredibly quickly. Something about carbon fiber causes aluminium to oxidize and fall apart. is like aluminium's kryptonite. This phenomenon is called galvanic corrosion, and it happens when two materials that have dissimilar electric potentials or nobilities are placed in contact with an electrolyte, like salt water. If we look at the galvanic series, which quantifies materials' nobilities, we can see that graphite is very noble, on the far end of the left scale, while aluminium is quite far to the right. When this occurs, an electric potential forms between the two materials that causes the two materials to trade electrons and ions, which results in the anode being eaten away. This effect is made even worse when the surface of the more noble material, the cathode, is very large in comparison to the less noble material, the anode. Say, for example, when carbon fiber composites are fastened together using aluminium fasteners. To avoid this corrosion, the engineers needed to pick a material closer to carbon in the galvanic series, and the closest suitable metal was titanium. This has been a huge source of cost in manufacturing. Boeing's production cost was higher than its sales price for quite some time, meaning they were making a loss on each aircraft sold. This is fairly typical for new airliners, as R&D and manufacturing tooling costs take time to recoup, and companies like Boeing typically spread these costs over a period of time on each plane, instead of just having a massive negative balance sheet in 1 year. But because the 787 was so radically new, these sunk development costs, called deferred costs, were expected to reach $25 billion before Boeing even reached a break-even point on each plane sold, where the cost of manufacturing equaled the sales price. In comparison, the Boeing 777 reached $3.7 billion. To recoup costs as fast as possible, it was essential that Boeing reduce the cost of production, and high on their list was the elimination of titanium parts where possible. The frame around the cockpit windows, for example, were initially made out of titanium, but were changed to aluminium with a special coating to prevent corrosion, while some parts that were originally titanium were changed to composites, like the door frames. Other improvements were sought to make the manufacturing process for titanium less costly. Many metallic parts used on aircraft start off as large blocks of metal that have to be machined down into their final shape. This results in a ton of wasted metal as the metal is gradually shaved away. Aircraft manufacturers quantify this wastage with something called a buy-to-fly ratio, and it's a huge source of increased manufacturing costs. Costs that Boeing has tackled by collaborating with Norsk Titanium, a titanium 3D printing company. Now, making 3D printed metal parts is not easy. Most titanium 3D printing involves a powdered titanium that is melted together using lasers. Researchers used high-speed X-ray imaging to visualize what happens during this process and found a lot of imperfections. The track varies in height, the powder gets blasted away, resulting
We're all soldiers now.
Oi! This is no time for standing around. Yeah! Ever get that feeling of deja vu?
5, 4, 3, 2, 1. Round 1. Capture the objective.
I'm not a young man anymore. down and I'll keep getting back up.
Meteor strike!
Be right back. Guys, located.
Knock me down and I'll keep getting back up.
Surrender to my will.
Apagando las luces.
Anna, checking
Knock me
in.
down and I'll keep getting back up. Damn it! Oh, behind you!
I might need this later. Damn it.
Is that melody? I don't quit till the fight's done. I've got you in my sights. I can do this.
Meteor strike!
Heal up here.
This will help. Minimal damage. The pain.
No rest for the weary.
Nano boost of my ultimate is almost set.
I've got you in my sights.
Double boom. Nano boost is ready.
Apagando las luces.
What is that melody?
Last round. 1. Score 1-0.
Stay out of our way.
Hey, I'm gonna set a teleporter straight ahead.
We need a moment to ensure all our equations are correct.
Schaden verstärkt.
Five, 4, 3, 2, 1. Round 2.
Teleporter
Capture
online.
the objective.
Move swiftly.
The objective is now. Objective.
through.
I'm on fire.
Reality bends to my will.
I've got you in my sights.
I have found the enemy. Come and face me.
Check your head.
Now let's break it.
This old dog's learned a few tricks. Tactical necessity.
Victory. Play of the game.
Apagando las luces.
The Trinitarian sing for me.
Double.
In varying thickness and separated tracks, and even bubbles form, causing pores in the metal. This creates parts with a lot of micro imperfections, and imperfections lead to decreased life as fatigue causes cracks to form. We can visualize a material's fatigue strength by plotting on an SN curve, which places the magnitude of the alternating stress on the y-axis and the number of cycles it survived on the x-axis. For traditional machined titanium, it looks something like this, whereas for 3D printed parts, it looks like this. 3D printed parts simply fail much sooner because of these tiny imperfections. Norsk has worked to improve this. Instead of using laser sintering with powder, Norsk have developed a revolutionizing, patented, wire-based metallic 3D printing system for titanium that they monitor with 600 frames per second cameras for quality control. These 3D printed parts are then machined down into their final shape, reducing the total titanium used by 25 to 50%, and their printing method is 50 to 100 times faster than the powder printing method. This process resulted in the first ever FAA certified 3D printed structural components, and they first flew in the Boeing 787. This plane is truly innovative.
Ooh, tomato, unpeeled with seeds, horrible for you because that's where the lectins are.
Titanium was not the only material Boeing worked on removing from the plane's construction to save on cost. Copper once formed an important part of the 787 wing, where it was laid down in thin strips on the wing's surface. This is not a typical design choice for aircraft wings, and once again it was influenced by the 787's composite construction, because composite materials are not good conductors. Carbon fibers are great conductors, but problems arise because of the plastic resin binding them together, as this resin is an insulating material, preventing the passage of electricity, which is a massive problem for planes, as getting hit by lightning is not a rare occurrence. One study calculated that lightning strikes occurred once every 3,000 hours of flying between 1950 and 1975. A 787 was struck by lightning while taking off from Heathrow. Upon landing in India, 42 to 46 holes were found in the fuselage as a result of resistive heating. The plane survived and was flown back to London for repairs with no passengers aboard, but composite's vulnerability to this kind of damage is a drawback, and the repair process is more complicated than with aluminium. However, this strike could have been much worse. If the electricity does not run smoothly along the surface of the plane and exit, it may cause a spark in the fuel tanks and cause an explosion. This kind of accident was not uncommon in the early days of the airline industry. Pan Am Flight 214 was struck by lightning while it flew in a holding pattern, waiting for a lightning storm to pass at Philadelphia International Airport in 1967. Its left-wing fuel tank exploded, causing the plane to barrel out of control to the ground in flames. Since then, the aviation sector has implemented rigorous safety measures and lightning protection tests to ensure an accident like this could never happen again. Early 787 wings were designed with copper strips to ensure the electrons had a path of low resistance along the surface of the wing, ensuring they wouldn't travel to the fuel tank and cause a spark, while also preventing resistive heating damage to the composite structure. Fasteners were sealed with an insulating material to stop electricity from traveling down the metallic fastener into the fuel tank, and the fastener themselves were fitted with compression rings and a sealant to eliminate potential spark locations caused by gaps and sharp edges. Finally, the 787 has a nitrogen inerting system that fills the tank with nitrogen. Ignition can't happen without oxygen. Boeing has since removed 2 of these protections in a cost-saving measure, removing the copper mesh and insulating caps, which drew concern and criticism, but Boeing argues that between the nitrogen inerting system and the other safety measures, these expensive features were not needed. Where composites couldn't be used, other materials were chosen. The leading edge of the wing and tail, the tail cone, and parts of the engine cowling were all made from aluminium or other metals. The leading edges of the plane needed aluminium because of composites' poor impact resistance. While composites have extremely high strength, they can be brittle on sudden impacts, such as bird strikes, which most commonly happen at the leading edge of the wing or on the engines. Metals are able to deform on impact with a reduced chance of fracture, instead of shattering as composites would. Aluminium leading edges were also beneficial for the purpose of de-icing because it is a good thermal conductor. If you have ever flown on a very cold day, you may have seen a truck spray fluid onto the wings of the plane. This is de-icing fluid, a heated mixture of glycol and water. It's needed because most planes aren't capable of de-icing themselves on the ground. The 787 can when fed with external power because it uses a new type of de-icing system. The 787 uses electrically heated blankets bonded to the surface of the slats, which are able to heat the surface of the wing and melt or prevent any ice formation on the leading edge of the wing. Traditionally, ice is prevented by extracting hot bleed air from the engine and piping it to vulnerable areas such as the leading edge of the wing, where ice buildup could severely interfere with the wing's operation. This draws valuable energy away from the engines and increases fuel consumption, while also requiring a complicated network of tubing and exhausts which add weight and increases complexity of construction and maintenance. The electric heating system is twice as efficient as the extracted bleed air system, as no excess energy is lost through venting air to the atmosphere, and it also reduces drag as the exhaust holes for the bleed air on the lower side of the wing create drag. The 787 is actually the first commercial airliner that has eliminated this bleed air system, which was a huge technical challenge and required a complete redesign of several systems and an entirely new engine. In our next video, we are going to explore the incredible engineering behind the power systems of the 787, exploring the advancements in the jet engine and the overall system architecture that allowed the 787 to become the most efficient long-range airliner ever made. We will be releasing that video here on
Goodbye endless spam calls. Hello to a phone plan with built-in spam blocking. See you later. Networks that are unsafe.
Traveling to Iconman. Prepare your defenses. Select your hero.
We're all soldiers now. I'm in no rush.
Right beside you.
Attackers incoming in 30 seconds.
I
1. Attackers incoming. Defend objective A.
Move out! Powered up.
Jeez, pushed up.
Objective lost. Stop the payload.
Knock me down and I'll keep getting back up. Technical necessity.
Der Kampf ist noch nicht vorbei.
Hatched up.
This will help.
Much better. I've got you in my sights. That's better. Don't see me angry. The war goes on. Should have kept your head down.
Der Kampf ist noch nicht vorbei.
Enemies re-engaging.
You should be at peak
Good
performance
choice.
level.
Enemy seen.
Helden sterben nicht.
I'm just getting started.
Moira by your side.
This old dog's learned a few tricks.
Oh no. All behind. Watch out, Hog. Hog, back here.
Don't worry, my friend. I have your shield.
Nice, Hog.
Seconds.
Anyone needs some healing? Someone had to do it.
Hog's coming up here.
30 seconds remaining.
Personne n'échappe à mon Symmetry reporting. I cast this forth.
This will heal you.
60 seconds remaining.
I've got you in my sights.
Everything in its place.
Score 0-2. Switching sides. Prepare to attack. Select your hero.
We're all soldiers now.
is not my preference to see to matters personally, but I will see them done.
He does look a little dry. Pecs look bigger,
Attack
but they kind of look
commences
softer.
in 30 seconds.
Delts look bigger as well. Arms might be bigger.
Stick together. We will complete
Go to the
our
side,
mission.
friends. And this is that midsection exposed.
Quit screwing around and get ready to
On the
move.
side, he looks like he had about 10 meals too many. 10 or 11 meals too many.
5, 4, 3, 2, 1. Attack commencing. Capture objective A.
I will get us home safe.
I require assistance.
Thank you, kind.
I'm not a young man anymore.
Justice ain't gonna dispense itself.
Get into position. Ladies and gentlemen, start your engines.
Rest in peace. I've got unfinished business.
Objective A.
I am on fire!
The payload.
Come here and get burned.
Rest in peace. Pardon me.
I'm restoring you.
Session is started.
Payload secure. Move out.
That was weak.
Back in the saddle again.
This will
Tactical goggles activated.
Austin.
60 seconds remaining.
Helden sterben nicht. Yahi param vastavika hai.
30 seconds.
What time we had is fading.
It's hand.
Over the minor setback.
It's hand.
I'll patch you.
10 seconds.
We're out of time.